Our next step in our journey through logic is to talk about the converse. So we've talked about implications. So we talked about P implies Q. Well, when we do that the opposite direction, so we look at Q implies P, that statement is called the converse of our original implication P implies Q. So an example of that, if 5 is an even integer, then 7 is an odd integer. That's true because 5 is not an even integer, so it's vacuously true. Now, if we look at the converse of that statement, then we look at the Q statement first. So if 7 is an odd integer, which it is, that's true, then our P statement of 5 is an even integer. Since 5 is not an even integer, we have a true statement implying a false statement, making the implication false. So here's an example of a place where the original implication is true and its converse is false. Now, one of the things that we do a lot with the converse is we take the conjunction of that converse with the original implication itself. So we have P implies Q and Q implies P. So when we do that and we put the two together like that, what we're doing is we're making the biconditional. So we write that with an arrow going both directions. So whenever we explore a new topic with logic, we should be interested in its truth value. That's one of the things that we really want to care about. So we want to look at when the biconditional is a true statement. So to do that, we're going to break it down into the implication, the original implication itself, and its converse, and then look at the conjunction. And we know truth table values. We know truth values for the implication, and since the converse is an implication as well, we know truth values for it, and we know truth values for a conjunction. So we can take all of the things that we know and put it together to generate a truth table for a biconditional. So remember, implications are always true except when we're taking a true statement implying a false statement. So when P implies Q and Q is false, P is true, then we have a false statement. And with the converse, whenever Q is a true statement and P is a false statement, so in this case right here, we'll have a false statement. But otherwise, implications are true. Either they're vacuously true or they have a true statement implying a true statement. So now, conjunctions, remember, they were true when we had both statements are true. This is the one that says it's this and this. This is the my name is Kayla and my name is Dr. Blyman. And if both of those are true, which they are, then I have a true statement. So both of my implications are the two sides of my conjunction. So now I'm not really looking at this initial part of my truth table anymore. I'm looking at the original implication and its converse, and I'm looking for a pair of true values. So when I do that, I have true and true here, and I have true and true in my last row. And otherwise, one of the two statements is false, and since they're being joined with that and in a conjunction, they both have to be true for it to be true. So now that we've done all of that work, now we're allowed to take out this middleman and all of the extra middle stuff that we did, and we can use our biconditional notation, use our first two columns, so we have truth values for P and Q, and we have truth values for the biconditional that go with it. So notice that the biconditional is true whenever P and Q have the same truth value, whether it's true or false. If they don't have the same truth value, then the biconditional is false. So one of the ways that'll help you remember that is to think about the words, the ways we can describe the biconditional, other than using a word biconditional. So ways that we'll say this a lot of times is P is equivalent to Q, or P if and only if Q, or P is a necessary and sufficient condition for Q. So especially that first statement, P is equivalent to Q. If two things are equivalent, they're going to have the same truth values. And so since that's the case, if P really is equivalent to Q, then they'll have the same truth values. So for the biconditional to be true, for the statement to be true, they both have to have the same truth values. So here's that, going back to that original example that I had, the biconditional way of saying it is 5 is an even integer if and only if 7 is an odd integer. So you notice that, and 5 is not an even integer, so the first statement is false. And 7 is an odd integer, so the second statement is true. So those two statements are not equivalent, and therefore the biconditional is false. On the other hand, if we change that word even, so we have 5 is an odd integer, which is a true statement, if and only if 7 is an odd integer, which is another true statement, then we have two things that are in fact logically equivalent.